Hi, my name's Tony Hiatt, and we're going to be talking about energy management today. It's a very big field, so we're just going to be touching on some of the high points of it. So any of these things we're talking about, you could probably spend a career on. So we're just going to hit the basics and go from there. So this is, again, like I said, this is just looking at some of the functions that are loosely called energy management. If you talk to energy managers or anybody in the energy management field, everybody may have a different idea of really what energy management is, because it encompasses so many things. And if you talk to someone on the street and told them energy management, they would probably just glaze over and have no idea what you're talking about, because it's one of those things where you really have to get into it to find out what's going on. So again, I'm Tony Hiatt. I've got a degree in mechanical engineering from Utah State, and I teach some of the courses in the energy management program here at Salt Lake Community College. So what are we going to talk about? We're going to start with what is energy management. Then we're going to talk about energy sources and use, with the idea being that we need to understand a little about energy before we can manage it. We're going to talk about energy opportunities, energy conservation opportunities. We're going to try to understand energy use a little bit better. We're going to get into how do you do an energy assessment to find out how you use energy and how you can use it better. We're going to get into energy savings, basically demand-side management programs, and how we can use those to our advantage to get things done. And then we're going to look at the energy management outlook, how this industry is progressing and what kind of opportunities are available for people and companies to get into this. Before we get started, I want to shamelessly plug the energy management program here at Salt Lake Community College. As you can see from the slide here, it's an associate's in applied science. It's an 18-month program, meets in the evenings 3 nights a week. It starts every August, so a new cohort starts every August. So if you're interested, definitely look into it, because it covers all aspects of energy management, from the basics of energy management to renewables. There's several lighting courses, several HVAC courses. We talk about controls, we talk about modeling, all sorts of different things to do with energy management. Also, if you are looking at just a single course, for example, you want to find more about lighting and you just want to take one course, that's a possibility too. So anyway, it's something to keep in mind. Okay, what is energy management? I've got here 3 different definitions of energy management, because like I said before, it's something that it's just kind of a catch-all for a lot of things. So let's go through each of these and see if we can glean something from them. The first one, the efficient and effective use of energy to maximize profits and minimize costs and enhance competitive positions. If you notice here, this doesn't have anything in it about curbing greenhouse gases or things like that, but it's all about money, and that's kind of how things are. In an energy management field, we need to realize that when we work for a company, we're an energy manager for a company. These energy management projects are competing for money with all the other projects in a company. So they're going to be looked at on a return basis. And the good thing about energy management is it's quite easy to make the grade on a lot of these things, because we're saving energy, we're saving money in the future. A lot of these projects don't just end when you've finished them. If you replace lights in a building, when they're paid off, you're still making money after that date. So the simple payoff doesn't really matter. We're still making money. So they compete very favorably with other projects in the company. The next one, the discipline and measures executed to achieve the minimum possible energy use and cost while meeting the true needs of the activities occurring within a facility. Again, there's a lot of word salad going on here in all of these because it's difficult to pin down one thing. But something you can pull out of this is that we want to be able to meet the needs of a facility. We don't want to, I mean, it would be easy to reduce energy use by turning off the lights and turning off the heat. But that's not what we want to do. We want to make sure that we can still meet the needs of the facility with a lower energy use. And again, that's something that can happen. The last one is the predictive, organized, and systematic coordination of the procurement, conversion, distribution, and use of energy to cover requirements while taking account of the ecological and economic aims. And of all of them, this is probably my favorite because it talks about doing things in an organized fashion instead of just replacing a bulb here, replacing a bulb there. We get a baseline of our energy use. We make a plan to move forward, and we make sure that we meet that plan. Also, we realize in today's world that there are other aims for businesses. They want to be as sustainable as possible, and this allows us to do that in probably the most sustainable way you can is by not using energy. That's the best energy there is the energy that isn't used, and that's kind of what we're talking about here. So we've talked a little about efficiency. There's energy efficiency and energy conservation are actually two different things. They're used interchangeably a lot, but they are two different things. So energy efficiency is when you use less energy to provide the same service, and energy conservation is when you reduce or go without a service to save energy. So there's an example here on the PowerPoint. Turning off a light is energy conservation. Replacing an incandescent lamp with a compact fluorescent or an LED, which both use 75% less energy, that's energy efficiency. So both of those, they're different things, but they're both important. In this case here, it would be best to replace our lights with something more efficient, and also to have some to turn them off when they're not needed. So both of those have a place in energy management. It's not one or the other. We can use both of those to the most effect. So before we talk about energy management, we need to talk about energy. It's very difficult to manage something that you don't know that much about. So this section is on energy sources and their use. On the screen here, it's got an address for the EIA website. That's a very good site if you have any questions about anything energy. That's the place to go. It's a DOE site, so it's run by the government, and so you can copy and paste anything on there, but there's links to everything on there. If you have any questions, that's the place to go. First of all, let's look at a little chart here talking about where our energy comes from and how it's used. So on the top chart is the U.S. energy production, how we produce energy in this country, and the bottom pie chart is the energy consumption, how we use energy in this country. So you'll notice both charts are kind of the same, with the exception of the petroleum piece of the pie. You can see that we produce 17% of the petroleum, 17% of our production is petroleum, whereas when you look at the consumption, 36% of it is consumption. So obviously we import some petroleum, and that's the difference in the two charts here, is that the amount that we import. So you can see, if we look at consumption, we can see that 27% of our energy needs come from natural gas, 36% from petroleum, about 8.5% is nuclear, and that's all electrical production. And then I think I already said 18% of it's coal. So this is for all energy use in the U.S., so it includes transportation, electricity, heating, cooling, all those things are considered in this pie. One of the interesting things is the renewables chunk of this pie. If you look at either one of those, but let's look at the consumption piece on the bottom there. You can see that renewables are about 9% of the energy pie, which a lot of people, when they look at this the first time, they're kind of surprised that renewables are so low, because we hear a lot of talk in the media about renewables, and the truth is that we still use a lot of fossil fuels. We're talking that all the pieces, the petroleum, the natural gas, and the coal, those are all fossil fuels. So that's a big chunk of our pie. The nuclear obviously isn't, but that's a non-renewable source also. So when we break down the renewables, you can see that half of that is biomass, and then a good chunk of it is hydropower. So when we look at what a lot of us would think of when we talk renewables, geothermal, solar, and wind, that's really quite a small percentage of renewables, and it's maybe a quarter of the renewables or less, and it's a tiny percentage of the whole overall pie. So it's been coming on in years. We'll have a chart here in a minute that shows how that's been happening, but still it's starting at a very small sliver of the pie. So even if it increases a lot, we've still got a long way to go on renewables. So again, our non-renewable energy sources, there's four main ones that you saw in the pie there. The oil and petroleum products, natural gas, coal, and uranium. So most of our pie, the consumption piece was probably, what was it, 92%, 91 or 92% non-renewable. If we look at the renewable sources, we can see that the five most used renewable resources are biomass. That was half of the renewables. And that's wood and wood waste, municipal solid waste, that's just our trash, landfill gas and biogas, ethanol and biodiesel. So those all comprise biomass. Ethanol is, as you probably know, it's made from corn, and that's an additive to gasoline. It's 10% or so of most gasoline these days. So that's come on quite a bit in the last few years, but that's a big chunk of it. We've got hydropower, which was a big chunk of the renewables, but as we'll see in a second, it's not changing much. It's kind of is what it is at this point. Geothermal is great if you can find it, and it's something that goes 24/7, so it's a great resource to have, but it's difficult to find. Then we've got wind and solar, which we're all fairly familiar with. So here's a chart that kind of lays out renewable energy generation. This is just a little bit different than the other charts, because this is talking only about electricity generation, where the other pie chart was all energy use. So now we're just looking specifically at electrical generation, what energy, renewable energies we use to generate electricity. And as you can see from this chart, a big chunk of it is hydropower. What is that? Almost 80,000 megawatts which is a lot of power, comes from hydro. If you look at the next one is biomass. That's usually, a lot of the biomass comes from paper plants where they use the pulp products to generate electricity, and wood products at a wood mill or something like that. So that's where those come from. There's a little piece of geothermal, but you can see hasn't really grown much from 2000, just because it's difficult to find the resource and very expensive to develop the resource. But wind, you can see the blue wind piece has really increased since 2000. It's just a little sliver in 2000, and now it's a big chunk in 2012. And the other piece, there's a little CSP, concentrated solar power, which is, those are plants where you capture the heat of the sun to heat water and to make steam and run it through a regular turbine setup. There's a new plant just outside Las Vegas. I think it's just across the California border that uses that. It has mirror farms that concentrate the sun's rays into a tower, make steam, and use that steam to turn a turbine, turn a generator, make power. So that's what concentrated solar power is. And then the top piece, the yellow piece, is photovoltaics. And I think we've all seen that, well, you just have to look at the chart. You can hardly see it in 2000, and now it's a fairly big chunk in 2012. So that has come on radically in the last little bit. Both farms, a utility scale PV, where a utility will build a farm out in the desert or something, to panels on people's homes. It's really come on in the last couple of years, and that has to do with the price of solar panels has dropped. Probably from 2000, it's probably dropped 80%. So anyway, that's looking at the renewable piece of it. So let's talk about energy conservation opportunities. There's a couple things we need to look at when we're trying to conserve energy in a building. And in this case, in this first case here, we can be talking about an industrial building or commercial or residential. In a building, we want to look at the building envelope. Buildings use a lot of energy in this country. I think it's approximately 40% of the entire energy pie is used in buildings. Heating them, cooling them, lighting them, all those things. So buildings use an enormous amount of the energy that we use. When we're looking at the building envelope, we've got to consider there's several ways for energy to enter and leave a building. There's convection, there's conduction, and there's radiation. For most of our heating needs, convection and conduction are the two things we're looking at. Radiation comes to play when we're talking about cooling a building, because we get a lot of heat gain from the sun, so we have to look at the radiation piece. But those are the three pieces we're looking at when we're talking about the building envelope. And so we want to have a tight envelope where our heat is not escaping from our envelope, so we don't have to provide as much heat to our building to keep it the temperature we need it, or cooling in the summer. Either way, we need a tight building envelope. I think there's also, in this series, there will be a couple of videos concerning building envelope and later infiltration that we're talking about that may be of interest if you want to go deeper into this. So our building envelope depends on the building characteristics and construction. A lot of homes that were built even in the 70s were not built very well, and so it's difficult to get a tight envelope when the original building was not that good. And so that in new construction, that's what we really have to look at, is to make sure that our envelope is tight. There's no places for our heat to escape. Also, there's window and door characteristics. We want to get tight-fitting, insulated windows and doors so we're not losing energy that way. Also, there's the insulation status, where we need to have enough insulation in our building, and we need to have it put in properly. Improperly installed insulation is far worse than you would think. You know, if it's even if it's installed a little bit incorrect, you can lose a lot of heat because now you've got path for the cool and the heat to get into the house. So it's got to be very specific how it's installed. It's got to have enough, and it's got to be installed right. I mentioned before infiltration. That's the other big piece of the energy puzzle for when you're talking about a building. It's the unintentional or accidental introduction of outside air into a building, typically through cracks in the building. Sometimes I guess it is accidental, but a lot of our buildings in the past were built not so great, knowing we would have some infiltration and relying on that to get fresh air into the home, which probably, well, definitely isn't the best way to go. It would be better to build a tight home and then introduce the fresh air as needed while you're taking the energy out of the air that's leaving the home. When you just build a building that's leaky, you're counting. You can't control anything. You know, the wind blows hard, and all of a sudden you've got more infiltration than you want. We'd rather control the fresh air into the home. One thing that you can do in a residence, as you can see on this slide here, they've got a blower door installed where you remove the door and put in this blower door with a fan in it, and it's got some devices to measure the pressure. So using that, you can pressurize or depressurize the home, and you can measure with these devices what kind of infiltration you're getting into the house. Whether you can tell how tight the house is, you can calculate how much air is coming into the home. So that's probably the best way to figure out how much infiltration you have, is with a blower door test. Let's talk a little bit about HVAC systems. Again, there's another video in this series that concentrates on HVAC systems, so if you have a desire to know more about this, I definitely look that up. But heating, ventilating, and air conditioning systems, they're in use in every building, whether it's a residence or commercial or industrial. And so a lot of the energy that's used in a building is used by the HVAC system. So we need to be aware of the performance rating of our system. For example, in your house, it would be better to get a high performance furnace, a 95 plus furnace, where you're using most of the heat that's in that natural gas to heat your house. You're not sending much up the stack, versus you get a less efficient furnace and it may be 80% efficient. You're 20% of the heat value of that natural gas is not being used. So you would much rather have a system that was more efficient for lots of reasons, not the least of which is cost. There's different equipment types, different ways to heat your homes. There's radiant heat, there's forced air, there's all sorts of things, and you need to examine which is going to work best for you. But one of the main points is, no matter what system you have, it needs to be maintained, and in a bigger building, in a commercial or an industrial building, it needs to be commissioned. That is where the mechanical contractor, the the contractor has installed the system. Now you need someone to tweak it and make sure it's working how it was designed. Just because it's installed doesn't mean it's going to be working correctly. All the different settings have to be made to get it working as it was designed. So that's a very important part of setting a system up. And then once a system's set up, that doesn't mean it's going to run that way forever. It may have been commissioned fabulously to start with, but over the years things change, equipment changes, people change, a lot of things happen. So you need to go back in and recommission buildings on a regular basis, where you look at how the building operates, how it was designed, and how you want it to work, and make sure your system is giving you that. That's probably one of the best ways with HVAC to get an improvement, is the recommissioning piece of the puzzle. And as we'll talk later, there are incentives. Utilities will give incentives to companies to do this kind of thing if you meet the criteria and jump through the right hoops. So we'll talk a little bit about that. There's other various industrial systems that you can save energy on, and we'll talk a little bit about those. One of the biggest is motors and drives. So motors are used a lot in industry. I mean, there's motors everywhere if you go into some kind of a industrial facility. If you have a larger motor that's older, it may pay to replace it with a more efficient motor. There's been, in the last 10 or 20 years, there's been a lot of efficiency gains in motors, and if the motor's large enough, it may pay to replace this motor with a more efficient one. Motors run a lot, and it doesn't take a big efficiency gain to earn your money back on a motor. The other thing that we'll talk about is the variable frequency drives, VFDs. If you know anything about AC motors, most of the motors that are in use today are induction motors, and those motors, they go at a certain speed. They go at 3,600 RPM, 1,800 RPM, 1,200 RPM. Those are the main speeds, but that's the speed they go at. It doesn't really matter. You can reduce the voltage, reduce the current. It won't change the speed. It will screw up your motor, but it won't change the speed. So they're built to go at one speed. What a variable frequency drive does is it can change the speed by changing the frequency of the electricity you're supplying to the motor. So the electricity that we get in this country is 60 hertz. So that means that every second your voltage is going from positive to negative, doing that 60 times a second. So what we do with the variable frequency drive is we change that frequency. So instead of 60 cycles a second, we change that through the electronics of the device to 30 cycles a second. So every second we're going positive, negative 30 times. What that does, it is essentially lowers the speed of the motor in half. So you go from 60 hertz to 30 hertz, you're going from 3,600 RPM to 1,800 RPM. And so by changing the frequency, we change the speed of our motor. So how does that help us? Intuitively, we can see that it makes sense that if we slow something down, we're going to use less energy. But it's actually better than that. If we've got a motor fan combination or a motor pump combination, the power that this thing uses is proportional to the cube of the speed it's going. So if we can reduce the speed a little bit, we affect the power a lot. If you look at this chart here, you can see what we're talking about. So if you reduce the speed, if you look on the bottom there, if we go from 100% speed to 80% speed, so we reduce the speed 20%, we're not reducing the power used 20%, we're reducing the power that we use 50%. And if we can reduce the speed from 100% to 50%, we can reduce the energy that this motor is using by 80%. So it's a really great return if we can slow these things down. And obviously, if you need the full output of a motor, you need the full output of a motor. But in a lot of cases, in fan and pump systems, you didn't need the full output of the motor all the time. It's just there was no way to change the speed. So what you did is you put in a valve and throttled it back, or some kind of a damper on a fan system, which essentially what you're doing is just wasting that energy. Make sure you don't, you don't want to have too much pressure on the other side, so you put in a valve, and you're just creating a lot of friction and using up that energy to get the pressure that you want. If we can use variable frequency drive, we'll just slow down our motor to give the output that we need. And that way we're not wasting energy on the one hand, and we get such a good return on slowing something down even a little bit, that variable frequency drives are useful. It used to be you had to have a fairly big motor to make it work out financially, but the price of a VFD has come down a lot. So now even on smaller devices you can get a VFD and really tightly control what your motor's putting out and save a lot of energy in the process. So those kind of things are very important. Another thing that we can look at is combined heat and power. And as you can see from the slide here, it's a CHP system it's not really a separate system. It's just combining two systems. A system to generate electricity and also use that thermal energy. In the past, those things were separated. Would generate electricity, would generate thermal energy to heat. But in a lot of cases, when we make the electricity, we have some heat left over, and instead of just throwing it up the stack, we can use that to heat our facility, to heat water, to do other things that we need. So as you see on the bottom here, it says, while the conventional method of producing usable heat and power separately has a combined efficiency of 45%, if we can combine those two, we can get levels as high as 80%. And CHP is becoming a big deal these days because there is we can do so much with it. In our Introduction to Energy Management class, we went on a field trip to the University of Utah and looked at all their systems up there. And one of the things they have is they have a gas turbine where they can generate their own electricity when they need it, and for various reasons. But one of the things they've done is, instead of just running that hot gas through there once and out the stack, they use the thermal output of this gas turbine to heat buildings around campus. They have a lot of heat needs, and so they can heat water and heat the buildings around the campus. So they get a much higher efficiency by combining those two things than separately looking at them. So it's a very exciting part of energy management. Lighting is a big deal in energy management because we use a lot of power on lights. So we want to reduce that as much as we can. If you look at the chart here, it talks about energy use in commercial buildings. You can see that lighting after space heating, lighting is the biggest cost in a commercial building. It says 21% here on the chart. So if we can reduce that by various means, it's probably the biggest bang for your buck, the lighting piece of this puzzle. Just because of the new technology that's coming out and the fact we use a lot of lights. So some of the ways we can reduce energy in our lighting is we can reduce the illumination levels, and to do that we need to do a lighting survey and start with what we need and go from there. A lot of buildings are quite a bit overlit, so you can use less light to get the same, cover the same need. And there's other ways of lighting. We can do some task lighting where if I'm using this desk, I don't need to light the entire room. I need this area lit. So we can look at task lighting. We can look at other ways to reduce the illumination levels to something that we need and not over illuminate something. We also can improve our lighting system efficiency, and we do that by using different types of lights. So for example, in an older building, it was fluorescent lighting, the big T12 tubes, which there's a lot better things now. There's the T8 tubes, the smaller tube. There's the T5 tubes that are even smaller still. And with the electronic ballasts, you can really cut the energy use in a building by getting new lighting. Also, there's compact fluorescents. I'm sure you've seen those with little swirly lamps, and now LEDs are really coming on. They're really here. They're not in the future. They are here now. In fact, they're rapidly replacing CFLs. So LEDs are the next big thing. And if you've been to Home Depot or Costco lately, you'll notice that's what they're selling. They're selling LEDs, and they're selling them for a pretty good price. They used to be quite expensive, but now they've really come down in price. And if you look closely, some of that cost is being borne by the electric company, the electric utility. They will jump in mid-market and buy down the price of this lamp before you see it. So instead of $10, it's $5. And we'll talk about why they're doing that. It's not because they're just so nice. There's a reason why they do that. So the price has come down quite a bit. Curtailing operating hours, that would come under energy conservation, where lots of rooms now have a sensor. Light turns on when you go in, the light turns off when you go out. So we're getting the light when we need it, but we don't leave the light on all day when we don't need it. So we can curtail operating hours. And we can take advantage of daylighting. There's lots of places, some big warehouse stores are putting in a lot of skylights so they don't have to light so much. And there's other places that are lit by daylight and don't need lights on all the time. One example is that I do lap swimming during the day sometimes. Spend some time on my back doing backstroke, looking up at the lights. And I've noticed that the swimming pool has all sorts of windows in it, and it can be the middle of the day and it's very well lit and the lights are still on. And there's really no need for the lights, so it would be much better to have some kind of a sensor that notices, that senses when there is enough light and turns the lights off. Those kind of things can really affect your lighting budget. We've talked a little bit about lighting replacement options. Our typical incandescent bulbs that we've all used forever, they put off light, but they put off a lot of heat. 90% of the energy in this bulb is used as heat. So it's like the light is almost a byproduct of the heat. So there's other options out there. There's the energy saving incandescents, which are, you can save about 25% on those. But the two main ones are the CFLs and the LEDs. Again, the CFLs are the little curly lights, and they can save 75% over an incandescent, and they last up to 10 times as long as an incandescent. But LEDs are kind of becoming the light of choice these days. You get about 75 to 80% energy savings because these lamps, they're just putting out light and not much heat, so you can save a lot of energy that way. The LEDs can last up to 25 times as long as a comparable incandescent. So and the price has come down to where it's something reasonable, and you can get dimmable LEDs, so it's really something that people need to look at these days. Definitely in a commercial space, but also in your home. It's to the point where you can really save a lot of money, and it'll make sense to buy LEDs for your home. Well, let's see if we can understand a little bit more about our energy use. For those of you that have taken physics, you'll recognize this energy balance. It's roughly the first law of thermodynamics, that the change in total energy in the system equals the energy you add to the system minus the energy you remove from the system. So you can do an energy balance in any system usually being a building, something like that, to figure out where your energy is going, because you can't create energy, you can't destroy energy, so it's got to go somewhere. So if you do an energy balance, you can figure out where your energy is going. And if we're going to talk about energy management, where we're obviously talking about managing energy, we need to measure it, because as it says here, what gets measured gets managed. So if you don't measure something, it's very difficult to manage it. You can replace a bulb here, change a motor there, do those kind of things, but if you don't have some kind of a baseline where you know how much energy you're using going in, and you make some changes, you can see what the result of that is. It's very hard to actually manage this energy. It's more hit and miss, which is better than nothing, but it's much better to have a system where you're managing this. So to do that, we need a baseline. We need to determine our energy use. So there's several ways of doing that. The best way would be to have a meter that says this is how much energy you're using. That's not always possible because lots of buildings or factories or stores just have one meter coming into the place, so you know how much energy the facility is using, but you don't know how much energy each piece of the facility is using. So a lot of places are becoming more sub-metered, where you get sub-meters around the building so you can see what each piece is using, and that's very helpful. A lot of buildings these days have a building management system where it's all computerized, where you can control things from the computer, control some things from your phone now, where you can see exactly what's going on. You've got sensors, you've got measurement throughout the building, where you can have a very good idea of what's happening. When you don't have those kind of things, you've got to do some estimates, you've got to do some calculations to figure out your energy use. And you can also do measurements. You can, for example, you want to know how much energy the device is using, how it's operating. You can put a measurement device on that system and let it run for a week or so and see how much energy it's using. So instead of making calculations, you're making direct measurements to see what's going on. As we mentioned before, utility bills is a very good place to start on all this stuff. You need to know what kind of energy you're using right now. So we'll talk about electrical bills first, and a lot of these bills can be confusing, especially if it's a commercial bill. There's all sorts of rate plans and things, so they can be confusing, but it's really important that you understand, so you make sure you're being charged for the right thing, and you can look at it and see what things are costing a lot, and you can fix them. So let's look at the parts of a electrical bill. There's the service charge, which is a flat fee that you get charged for being part of the system. There's the energy charge, which is what it sounds like. You're getting charged for how much energy you use. And in this case, it's per kilowatt hour. So that's a measurement of a discrete amount of energy is a kilowatt hour. So if you use 1 kilowatt of power for an hour, you've used 1 kilowatt hour. The next piece, and this pertains to an industrial or commercial bill, is a demand charge, and that is measured in kilowatts. So a kilowatt is a measurement of power. It's an instantaneous measurement of power. So some people get confused on these two. So if you could liken kilowatts to your speedometer. Sometimes you're going 50 miles an hour, sometimes you're going 60 miles an hour, sometimes you're going 20. It varies as you're going. So that's what a kilowatt is sometimes you're using a certain amount of kilowatts, then you're using more, and it can vary. The energy charge, the kilowatt hour, is more like your odometer. You may have gone 20 miles an hour, 30 miles an hour, 50 miles an hour, but at some point you went 100 miles. So the kilowatt hour is measuring how much energy you've used, and the kilowatt is measuring how quickly you're using it. So a demand charge is what the utility charges you for how much you're using energy. For example, if you use energy at a certain rate and then all of a sudden you jump up to twice that and then back down to the initial rate, they're going to charge you a demand charge for that extra piece, because the way the electrical system works, they have to have generation available for you at your highest peak. And the way the electrical grid works is energy is consumed as it's made. It's not stored anywhere. It's got to be a match between what's made and what's consumed. So the demand charge is a way for the utility to charge you for the cost to them of having this generation available when you need it. If you can lower that peak, you can really cut your demand charge, and it can make a big difference on your bill. In some industrial commercial bills, the demand charge is as much as the energy charge, so you can make a big dent in it. Obviously, the demand charge doesn't have anything to do with using less energy. It just has to do with paying less money for it, which is important to most businesses. There's different rate structures. There's a flat rate where you pay the same amount for every kilowatt hour. There's a seasonal rate where you pay more in the summer than the winter. There's tiered rates where the first chunk you use is this much, the second chunk is more or less, depending on what kind of a rate you're on. And then there's time of use rates where there's periods of high demand during the day, during the evening, where you'll be charged more than something in the middle of the night where there's not that much need for the power. So let's look at a sample bill. So this is a residential electrical bill, and you can see a lot of the things that we've talked about on here down there in the list of items. You can see the first thing is the basic charge. That's $5 a month. Then you can see different charges for 2 different blocks, a different rate for each block. It looks like the first block is 400 kilowatt hours, and then it goes over into the next block. It looks like there's different rates for summer. The first 4 days were under one seasonal rate. The next 26 days were under another seasonable rate. So all those things are mixed up into this to give you the price that you're paying. You can see the energy charge for the summer block 1, 53 kilowatt hours, is about 8.9 cents per kilowatt hour. So it goes down, it goes up. The more you use, you get into the next block. Now you're talking, what's that, 11.5 cents kilowatt hour. So in this case, you use more, you pay more. I've seen some commercial ones where you use more, you pay less. So it just depends on the rate. The other thing you can see from the chart there, the historical data, is you can see how the energy is used over the years. And from this, you can see that most of the energy, again, this is the electrical energy, most of it is used in the winter, and it really goes down in the summer, which, just from looking at this, and since it's my bill, I know about it, that it doesn't have air conditioning. So if I had air conditioning in the summer, you would probably see the reverse of that. You would see more of this shape to it, where we're using more in June, July, August, September, if I had air conditioning. So let's talk about natural gas bills. So when we're talking about a natural gas bill, we're talking about the billing unit for a natural gas bill is a therm, or usually a decatherm. So a therm's 100,000 BTUs. BTU is just a measurement of energy. It's a very small measurement of energy. It's about the energy you get when you light a match. So it's a very small piece. The definition of it is to raise 1 pound of water 1 degree F. So it's a very small piece of energy, but it can be used for anything. So our natural gas use is measured by the volume, by the 1,000 cubic feet or million cubic feet. So it's measured by the cubic foot. And then there's a BTU factor applied to determine the heat content, because the quality of the gas changes, so we have to have a fudge factor for that. Let's look at a natural gas bill. This, as it turns out, is a commercial natural gas bill. So we have to look at the type of rate that we're on. This is a GS, so you can get from the utilities all the information about your rate, and you can look at that and see what the rules are for that rate. In here we can see that there's the basic service fee of $55. The charge for the gas used is about $2,000. And then at the bottom you can see that the gas is measured in CCF, and there's a multiplier applied before we can figure out the billed decatherm amount. So again, this you can see it's from the franchise fee tax that it's in Park City. So most of the use, almost all the use, is in the winter. There's some to heat water the other times of the year, but it's almost all in the winter. So again, it's very important to get a bill and figure out a baseline. So now we're going to talk about energy assessments, or some people call them energy audits. The purpose of an audit is to understand how the energy flows in the building and how it's used. And obviously that's not all we're looking for. We're looking for ways to reduce energy use. So that's the bottom line of this, is how can we reduce our energy use and not negatively affect our output. And then while we're doing this, the second item there, while we're doing this, we want to kind of prioritize the things we find. So if we can use, we want the low-hanging fruit here first. We want, if there's some things we can do to really affect our energy use, we want to do those first and work our way to the more expensive, more complicated things later on. So there's several types of commercial industrial audits. That's what we're going to talk about more, is the commercial industrial end of things. The first one is the benchmark audit. It's basically to find out how you use energy now, and we'll use that in the other phases of the audit. So one of the things you do is what we did when we were looking at the bill. We figure out our utility use, our demand, our peak demand, because that can really affect the bill, and the cost. We develop an energy cost index, which is a dollars per cubic foot of floor space, so we can kind of get a handle over on, is this building a pig? Is it very efficient? We need to have some measurement so we'll know where we're at. We can also develop an energy utilization index, which is that's BTUs per square foot. So that's the energy use. The energy cost index was the dollar use. So it just depends on how expensive your utilities are to the energy cost index. So the energy utilization index is really the most important thing, because that tells you how much you're using, regardless of what you're paying for your utilities. And then when you come up with that number, is that good? Is that bad? How do you know? So one thing that we can use is the EPA Portfolio Manager, and that's a program that EPA's developed, and now it's got a lot of information from all over the country where people have put in their information for their buildings, so you can compare your building to a building like it, because buildings can vary widely over their use. If you're talking about a hospital versus an office building, the energy utilization index is going to be completely different, because it's just more intensive. A hospital is very energy intensive. So and now one of the things we want to come up with is, how are we using energy in this facility? And from this pie chart, that's kind of what this says, is this is all the energy uses in this facility. So you can look at it quickly and say, man, heating, 28% of our energy use is heating. The next big thing is our process. We're using 18% of it. We can kind of look at everything, lighting, that's 1%, air compressors 1%. So you can easily hone in on, these are the big energy users. This will be the biggest bang for our buck if we can hit the big things first and then work our way out. So an end use breakdown is very, very helpful. I talked a second ago about Portfolio Manager, and this is some information from Portfolio Manager. When you use it, you can log in, put all your building information in there, and it'll give you all sorts of reports about your water and energy use and how that compares to other buildings. This is just a graph of all the buildings in the system, all the office buildings, and how they relate. So you can see that the median energy use is 207 kilobTUs per square foot, and then it goes out from there. So there's a wide variation in different buildings. So the use of the Portfolio Manager is to let you see how you compare with other buildings. The next step up in an audit is a level 1, which is a walkthrough survey, where you use your information you gathered before, you do some on-site surveys, you identify some of these low-cost, no-cost energy efficiency methods, and then you perhaps make a list of potential capital improvement projects. Things are going to cost money, going to have to be approved. Usually that takes a budgeting cycle, something like that, so you need to know early on what those are. The next level is the energy survey and analysis, and it says at the bottom here, this level of analysis will give you adequate information for most buildings and most measures. But it's just building on the one before, where it's just a little more rigorous. You gather your energy consumption and peak demand analysis. You do a breakdown. You identify these energy efficiency measures. You look at changes, O&M changes you can do to the operation and maintenance to use less energy. Those are definitely low-cost measures that you don't have to buy anything new. You just have to make sure the equipment you have is running properly. You can list these capital-intensive improvements that you're going to maybe need some more analysis on, and then you assess some potential costs and savings. The last one, the investment grade audit, is where this is for more capital-intensive things where you're going to need more information to get the money approved to do these things. So you need some more information gathering. You may need modeling, simulation of the buildings. There's several programs. There's Energy Plus. There's other programs that you can use. eQuest is one that's used a lot, where you can model a building. You basically build your building in the computer, and then using weather data and other things, you can model how this building is going to perform over the year, and then you can make changes and say, well, what if I add this? What if I take out that? And you can see what the effect will be. Obviously, building something like that takes some time, so it's got to be a fairly decent project. This investment grade audit comes up with much better numbers for how much this is going to cost and how much it's going to save, so that you can use that for budgeting purposes. And it often uses the life cycle cost analysis as a decision-making tool, where you look at the cost of this thing over the life of it, not just a simple payback of, I put this in, it'll pay itself back in 5 years. You want to look over the life cycle of this piece of equipment to see how much it's going to save over the life of it, and use that to decide whether you're going to do it or not. So energy savings. This section is about the demand side management piece that I mentioned earlier. Demand side management is utilities, usually electric utilities, trying to get you to use less energy. And again, the reason they're doing that is not because they're nice, not because they're stupid, trying to not get you to buy their product. It's kind of a weird thing. But they have figured out that if they look at how they need to supply energy to their customers, every resource has a cost to it. If you build a coal plant, it produces energy at a certain cost. If you build a wind farm, it's a little higher cost. So there's different costs for different resources. They've figured out that energy efficiency is their least cost resource. So if they can get people to use less energy and don't have to build a power plant, then that is their least cost way to provide energy to their customers. And that's what they're really required to do, is to provide energy at the least cost. So that is why they've set up these demand side management programs. You can see in here there's some of the reasons why they do that, to encourage you to do these different things. One thing I forgot to show you on the, let me go back real quick here, see if I can do that. If we go back to our bill, our electrical bill, we can see an item here for customer efficiency services. And you can see that's about 3.3, I think that's a percent. So about 3.3% of your bill is going to this customer efficiency service. And that is the money that they're using to run these demand side management programs. They're using that fee there. So basically, they're not giving you something for nothing. This is your money that they're spending for you to provide this service. So that's where the money comes from for this. Here's a list of some typical Rocky Mountain Power incentives. There are incentives for lighting and evaporative cooling and heating and rewinds, different things. They have several different programs, especially for industrial and commercial companies. They have programs where they will pay for the energy audit. They will give you incentives to buy new equipment. They will help you with recommissioning. They'll give you a certain amount for recommissioning costs. For companies that use a lot of energy, they have a project manager program where they can even provide money for you to hire somebody to make sure all these projects happen. So there's all sorts of things. If you've got a bigger company, there's all sorts of incentives that they offer through this demand side management that you can take advantage of. So that's something to definitely look into. Likewise, Questar does the same kind of thing. They have incentives if you want to upgrade your boiler, you want to insulate your water lines. They have incentives for those kind of things too. So if you're doing those things in your business, you need to check with the utility incentives and make sure and find out if that's something you can use. And that's not something you do on the back end to get paid back for things. Usually that's too late. It's something you do on the front end to find what services they offer, take advantage of those, and also the incentives on the back end. Now the energy management outlook. Again, we have just scraped the surface of this. Energy management is a huge field with all sorts of different subfields, and there's a lot of things going on. Some of the potential employers, there's energy consulting firms that a lot of those work for the utilities to do their incentive work. There's energy engineering firms, do kind of the same thing, but a little more on the engineering side of things. You can work for a utility company working in their demand side management. There's architecture firms. For example, they might model a building beforehand to see its energy use to make sure it's going to be where they want it to be, if they want it to be LEED certified, something like that. There's building management companies that run a lot of buildings. If you can save just a little bit in a big portfolio, you can save a lot of money. So there's building management companies, large industrial companies, people that use a lot of energy can save some money. Again, school districts, they have a lot of buildings that use a lot of energy. And there's all sorts of other things. There's renewable pieces to this. There's a lot of little arms in this energy management system. So to close, this is a very varied field. We've just given an overview. Obviously, there's going to be we expect a lot of growth in this industry. Sometimes it's hard in Utah because we're cursed with low rates for electricity and gas, so it makes the payback not quite as good as it would be somewhere with higher rates, but still money's money, and there is still growth in this field, and it's going to be a big part of our energy future. If you look at anybody's estimate of how we're going to reduce our energy use, how we're going to get there, energy efficiency always plays a big part of that, because like I said before, the best energy is the energy that we didn't use in the first place. So thank you, and I hope you enjoyed it.